Welcome to this video lecture on Statistical Process Control, SPC. Statistical Process Control is a technique for observing a process to make sure that it is doing its best and to see when adjustments are required. It operates in much the same way that a driver drives a car, by looking through the windscreen, making observations, and then adjusting the steering as necessary. In statistical process control, we observe the behaviour of the process by taking samples at regular intervals from the process and plotting those samples on a chart. And then the chart will tell us if some adjustment is required. Very small variations in the process are to be expected and do not require adjustment. And in fact, it's better not to adjust a process if there is no source of variation present. But we do want to identify when the process has changed so that adjustments can be made. Notice that the focus is on the process and not on the product. Our purpose in statistical process control is to make sure that the process is doing its best. If the process is right, then the product will be right. And so if there is a defective unit of material made, that's a different issue. We might want to apply some remedial action to correct that unit so that it's not disposed of. But statistical process control has a much greater ambition. Statistical process control takes a signal from the process that the process is not doing its best and deals with the underlying cause, so that there will be no future problems of the same kind in the process. If the process is right, the product will be right. A control chart consists of a time series plot of some process measurements, and then some limits are drawn on the chart at 3 sigma above and 3 sigma below the mean. Now, control limits are not specification limits. These are not limits that tell us whether or not the product is saleable. That's what specification limits do. That's the voice of the customer. Control limits are limits that tell us when the process has stopped doing its best. When the process is providing measurements that are 3 sigma away from the mean, that is, measurements that would be unlikely to arise if the process was doing its best. This is a lot like rumble strips along the side of a road. If a driver moves out of their place and the tyre goes across a rumble strip, the rumble strip gives some feedback to the driver through their steering wheel. And this alerts the driver that they need to take corrective action. They have begun to stray from doing their best and they need to take corrective action so that something worse doesn't happen. But a big problem has not yet occurred. The car has not crashed and the car has not left the road. But the signal is given early. It's given in time so that corrective and timely action can be taken to prevent a problem occurring in the future. So the whole idea with SPC charts is to identify when something is wrong with the process, then identify the cause of the problem and take action to address that cause in order to prevent recurrence. So it's future-oriented and it's process-oriented. Now, what are the issues that might require attention in a process that might give rise to one of these special causes of variation? The special causes can be summarised by these 6 words beginning with M, 6 M's. So when we get a signal in a process, we can look at these 6 M's and see what's likely to be the cause. The first one is men, by which we mean people, operators, who may be untrained or unmotivated or fatigued, and they are giving rise to a problem in the process. The second is material. The material may be defective, or it may be just different. Perhaps a different batch of material has arrived, and it is causing the process to behave in a different way. It could be the machines that are used to do the process, and the machines could be damaged, or they could be incorrectly adjusted, or they may require maintenance. It could be the methods that are being used. Maybe the procedures are not appropriate, or maybe the procedures aren't specified, or they're not being followed, they're being ignored. It could be the milieu, that is the environment. It could be the weather has changed, the temperature or relative humidity, or the utilities, the pressure in an airline or the voltage in a main supply. Or finally, it could be measurements. Measurements mean that the problem is not with the process. The problem is with the measurements that were made on the process. So the statistical process control chart is actually giving a false signal. It is telling us that something is wrong when nothing is wrong, or telling us that everything is okay when something is wrong. This is a particularly difficult one to deal with. When a process control chart gives an out of control signal, we still need to find out what it is that's causing the problem. The chart cannot tell us that. So we can use our knowledge of the process, which might be able to tell us what the problem is. Another good clue to what went wrong is the time at which a signal appeared. If a process is behaving well hour after hour after hour, and then at a certain time we get an out of control signal, this suggests that something has gone amiss in the recent past. It may not be in the time since the previous sample was drawn, but it could be over the time sometime during the time when the last 5 or 6 samples were drawn. And so the recent past is a clue. We can ask ourselves, what did we change recently in the process? It's also worth noting that sometimes a lower limit may represent an improvement in the process. If the number of defects or defectives goes down, this represents that the process has changed for the better. And we should identify the cause and make sure that we improve the process so that this new version of the process becomes the standard version from now on. The first chart we're going to look at is an individuals chart. It's the simplest type of chart, although not the most popular of all the charts. An individuals chart takes individual measurements from the process and plots them on a time series from left to right, and also puts control limits on the chart. We're going to look at the delay experienced by customers at a drive-through restaurant. So here we have the individuals chart. You will notice, like almost all SPC charts, it consists of a time series plot proceeding from left to right. So time proceeds from left to right. And of course there is some variation in the data. That's to be expected. There will be random variation in any process. But there are also limits drawn on the chart, the upper control limit and the lower control limit. And these are placed at 3 sigma away from the center line. So if an upper or lower control limit is violated, it's unlikely that that would happen if the process continues to behave at its best level of performance, if it continues to behave consistently. So if a violation occurs, and in this chart the final point has violated the upper control limit, this is a signal that the process is out of control. Something has changed in the process, and the delay for that customer was longer than would be expected if this process had continued to behave in the same way. So this is a signal that we should take action to identify the cause and take action to prevent recurrence. It's not a question, as I said before, of just compensating this customer for the delay. It's a question of finding out what has gone wrong with the process. And of course, what has gone wrong could be one of the 6 M's. It could be men. We could have an untrained worker working today. It could be material. Perhaps we usually get lettuce leaves supplied, but today we've got lettuce heads. And so that requires more time to prepare the order. It could be machines. It could be there's a broken drinks dispenser. It could be the methods. Perhaps there was a failure to start cooking the food before pouring the drinks, which would delay the preparation of the food. It could be the milieu. Maybe there's a reduction in the electrical supply voltage and that affects the cooking time. Or it could be the measurements. Perhaps we measured the time until the customer drove away instead of measuring the time until the food was delivered. And so perhaps there's no problem in the process and the measurements are indicating that there's a problem. The next chart we look at is an X-bar chart. An X-bar chart plots sample means, as the word X-bar suggests. So this is the bottle filling data that was also studied in section 8A when we studied process capability. So samples of 5 bottles each are taken from 30 different batches of a process and plotted on an X-bar chart. Now note that these points are sample means. They are not individual values. So these points that are plotted on this graph give us an idea of where the population mean is at any time. And of course there will be some rise and falls in the data to be expected, some random variation. But we want to know if the process is in control or out of control. So again, we draw the 3 sigma limits. Actually, 3 sigma over root n on this occasion, because these are sample means. And on this chart, we see at the end of the chart on the right, there are 2 violations indicating that the process mean has changed, that the fill volume has increased. And so we get a signal that the process is out of control. Now, the examples shown here show some violations, although during the normal use of SPC charts, we don't expect to see violations often. But in an educational setting, we want to show you what happens when a violation arises. The default approach with the software is to use the standard deviation within to calculate the control limits. But if we have an unstable process, then it would be more realistic to use the standard deviation overall. This is an X-bar chart, and it's probably the most popular of all the control charts because it's a simple way to keep a track of the mean of a process. And sometimes in conjunction with an X-bar chart, sometimes one keeps an S chart, a standard deviation chart, or an R chart, a range chart, to keep a track of the variation in the process as well. But here we just show an X-bar chart. The next 2 types of charts we will look at are both attribute charts. These are charts for data that is counted rather than measured. And the first one of these is called an NP chart. And an NP chart, as the name suggests, has a sample of size n and a proportion p of defectives. So an NP chart looks at the number of defectives or defective units in a sample of size n and plots that number of defectives from left to right as time passes. And the sample sizes should be large. There should be at least 5 defectives expected in the sample. Violation of an upper control limit will indicate that the proportion of defectives has increased. Violation of a lower limit will indicate that the proportion of defectives has reduced. And so, of course, a violation of a lower limit would be good news and would suggest an avenue for process improvement. NP charts are based on the binomial distribution, which you can study or may have studied in the past. So these are the number of late deliveries by a courier over 30 days. The sample size is 50. So out of 50 deliveries, the number of late deliveries is tracked every day, and this is plotted on a chart. And this chart indicates that the process is in control. There is no evidence that the process has changed and that the proportion of defectives has either increased or decreased. Now, you might notice that the proportion of defectives is high. There's quite a high proportion, about 10 out of 50. That's almost 20% of deliveries are late. And that, of course, could cause concern. But the purpose of a statistical process control chart is not to improve the process. It is to make sure that the process continues to behave at its best level. We can use designed experiments for improving processes. So we use SPC charts for monitoring a process, for making sure that the process is doing its best, whatever its best might be. And there is no use in demanding a higher level of behaviour from the process than what it's able to deliver, because this would not be sensible in a control chart. It just means that we would simply have violations all the time with no remedial actions, or no corrective actions rather, available to us. So a statistical process control chart is based on what the process is able to do and make sure that the process is doing its best. The next type of control chart we're going to look at is a C chart. A C chart, we're going to apply this C chart to the number of damaged bags at an airport each day over 30 days. Now notice that the number of bags at an airport could be any number in a day. We're not checking like 50 bags as we did in the previous example with NP. So this is based on the Poisson distribution rather than the binomial distribution. We have an interval of time, and within that interval we're counting how many defects occur. So a C chart is used for defects, while we've already seen that an NP chart is used for defectives. The thing about defects is that a number of defects can occur within the same interval. We are not counting a fixed number of yes-no outcomes. We are counting how many times the event occurred within an interval. Okay, so here we have the C chart with the values proceeding from left to right. And of course, as always, there is some random variation. And again, the sample size should be such that we would expect 5 to occur in each sample. And so we get a violation of a lower limit. But of course, because these are defects, this indicates that the process has improved. And so again, we can look at the 6 M's to see what might have caused this improvement. Could it be men, that we've got a new worker taking greater care? Could it be materials, that we have a reduced maximum allowed bag weight? Could it be machines? Perhaps a new carousel has been installed. Could it be methods, that there's a new procedure for handling the bags? Could it be the milieu? Maybe there's better lighting in the baggage reclaim area. Or could it be measurements? Perhaps there was a failure on this 30th day to record all of the damaged bags. So we see here with all of these SPC charts that they all provide a way to assess a process and see if the process has changed. Is the process doing its best, or does it require adjustment? And again, let me repeat, our focus is always on identifying the cause and taking action to prevent recurrence. So when setting up an SPC system, there are these questions we need to ask ourselves. First of all, what process parameter needs to be controlled? If we're filling bottles with liquid, do we measure the fill volume, or the fill height, or the fill weight, or the gross weight, or something else? So we identify what it is that's important to us. Secondly, which statistics should be plotted? If it's fill volume, shall we plot individual volumes, or sample means, or something else? Thirdly, how big should the sample be? And the answer to this question is a handful of measurements, about 5 measurements. Drawn frequently is better than drawing a larger sample less frequently. So a handful of data. Number 4, how will the samples be drawn? The samples should be drawn in rational subgroups. This means that the units within a sample should be as alike as possible. They should be taken close together in time and not mixed from different sources. There should only be unexplained variation within a sample. The 5th question is, how often will samples be drawn? And there are 2 answers to this question. It depends on whether the process tends to drift or suddenly shift out of control. If a process is prone to shift suddenly out of specification, the economic principle is that the cost of defective product should be the same as the cost of sampling inspection. So if we are spending more on inspection than we are losing on defective product, then we should do less inspection, and vice versa. In the case of a process that drifts at a predictable rate, when it goes out of control, we should have a sampling interval that's short enough so that if the process begins to drift, just after we have taken a sample, that we will be back to take the next sample before it drifts out of specification. 6th question is, how will the control limits be calculated? And the answer here is that we use the process data to inform us about what the process is able to do, and we base our control limits on the ability of the process, on the capability of the process. And the final question is, what response will be made to an out-of-control signal? And the answer there, and this is the most important question, is that the purpose of the out-of-control signal is to provoke us to take action to deal with causes, so that the process can be returned to a state of statistical process control. So we need to be clear about who is responsible for taking action. And if it's a different person than the person who maintains the charts, it's good that the person who maintains the charts would be made aware that action was taken so that they remain motivated to maintain the charts. You can read more about this in the textbook in section 8b.